Industrial machines used in manufacturing processes are classified as industrial machines and must be protected according to Article 670 of the National Electrical Code, or NEC. NEC Article 670.2 defines industrial machines as an assembly of two or more components, at least one of which is a motor, and that is intended to be used as a unit to perform a specific mechanical function. Article 670.3 mandates that industrial machines be protected against overload, short circuit, and ground fault conditions. The protection must be sized and located in accordance with the requirements outlined in Article 670. Overload protection for industrial machines must be provided by a device capable of interrupting the current when the load exceeds a specified limit. This device can be a thermal overload relay or a circuit breaker with a suitable trip curve. The overload protection device must be set to trip at a current value not less than the machine's rated full load current. Coordination is critical to ensure the overload protection device operates before damage occurs to the machine or downstream equipment. This means the rating of the overload protection device must be less than the rating of the next upstream protective device. Oversized mains can lead to a lack of proper coordination. If machines are not protected according to the correct code section, a qualified electrician should perform an assessment. The electrician can determine the appropriate protection requirements for each machine and make necessary modifications to ensure compliance with the NEC. They can also evaluate the electrical system's coordination to ensure it meets required standards. When evaluating the protection of industrial machines, it's important to consider several key factors to ensure both safety and compliance with the National Electrical Code, or NEC. Firstly, understand the specific requirements outlined in NEC Article 670, which governs the protection of industrial machines. This article provides detailed guidelines on overload, short circuit, and ground fault protection, ensuring that machines are adequately safeguarded against electrical faults. Secondly, accurately classify the machine according to NEC definitions. An industrial machine, as defined in Article 670.2, is an assembly of two or more components, with at least one motor, designed to perform a specific mechanical function as a unit. Correct classification is essential to apply the appropriate protection measures. Thirdly, ensure proper overload protection is in place. Overload protection devices, such as thermal overload relays or circuit breakers, must be capable of interrupting the current when the load exceeds a specified limit. These devices should be set to trip at a current value no less than the machine's rated full load current, preventing damage from prolonged overcurrent conditions. Fourthly, verify adequate short circuit and ground fault protection. Short circuit protection devices, typically circuit breakers or fuses, are designed to quickly interrupt high magnitude fault currents, preventing catastrophic damage to equipment and minimizing the risk of electrical hazards. Ground fault protection devices detect and interrupt ground faults, which can pose significant shock hazards and cause equipment damage. Fifthly, prioritize coordination of protective devices. Coordination ensures that the protective device closest to the fault operates first, minimizing the extent of the outage and preventing unnecessary tripping of upstream devices. This requires careful selection and setting of protective devices to achieve selective coordination, where only the faulted circuit is interrupted. Sixthly, consider the machine's operating environment and specific application. Environmental factors such as temperature, humidity, and corrosive atmospheres can affect the performance and reliability of electrical components. Similarly, the machine's specific application may require additional protection measures, such as surge protection or voltage monitoring, to ensure safe and reliable operation. Seventhly, perform regular inspections and maintenance of protective devices. Over time, protective devices can degrade or malfunction, compromising their ability to provide adequate protection. Regular inspections and maintenance, including testing and calibration, are essential to ensure that protective devices remain in good working condition and are ready to respond when needed. Eighthly, document all protection measures and settings. Maintaining accurate records of protection device settings, coordination studies, and maintenance activities is crucial for troubleshooting, future upgrades, and compliance audits. Documentation should include device ratings, trip curves, and any specific considerations related to the machine's protection. Ninthly, consult with qualified professionals. Electrical protection is a complex field, and it's essential to seek guidance from qualified electricians, engineers, or other experts who have experience in industrial machine protection. These professionals can provide valuable insights and recommendations to ensure that machines are protected according to the latest codes and standards. Tenthly, stay updated on the latest revisions to the NEC and other relevant standards. The NEC is updated every 3 years, and it's important to stay informed about the latest changes and requirements. This ensures that protection measures remain compliant and reflect the best practices in the industry. By considering these key factors, one can effectively protect industrial machines, minimize the risk of electrical hazards, and ensure compliance with applicable codes and standards. Remember that electrical safety is paramount, and any work on electrical systems should be performed by qualified personnel with the appropriate training and equipment. To further elaborate on the specific aspects of industrial machine protection under NEC Article 670, let's delve into more technical details. Starting with overload protection, it's crucial to understand the different types of overload relays and their applications. Thermal overload relays, for example, use a bimetallic strip or melting alloy to sense over current conditions. These relays are relatively inexpensive and simple to apply, but they may not provide the most accurate or repeatable overload protection. Electronic overload relays, on the other hand, use solid-state circuitry to sense over current and provide more precise and adjustable overload protection. These relays can offer features such as adjustable trip curves, thermal memory, and communication capabilities for remote monitoring and control. When selecting an overload relay, it's important to consider the machine's full load current, service factor, and duty cycle. The relay's trip current should be set no higher than the machine's full load current multiplied by the service factor, as specified in NEC 430.32. The duty cycle of the machine should also be considered, as frequent starts and stops can cause the overload relay to trip prematurely. Moving on to short circuit and ground fault protection, it's essential to understand the different types of circuit breakers and fuses and their interrupting ratings. Circuit breakers are electromechanical devices that automatically interrupt the circuit when a fault is detected. They are available in a variety of types, including molded case circuit breakers, insulated case circuit breakers, and power circuit breakers, each with different interrupting ratings and features. Fuses are overcurrent protective devices that use a fusible link to interrupt the circuit when a fault occurs. They are available in a variety of types, including plug fuses, cartridge fuses, and power fuses, each with different current ratings and interrupting ratings. When selecting a circuit breaker or fuse, it's important to consider the available fault current at the point of installation. The interrupting rating of the circuit breaker or fuse must be greater than the available fault current to prevent the device from failing during a fault. The NEC requires that circuit breakers and fuses used to protect industrial machines have an interrupting rating sufficient to interrupt the available fault current, as specified in NEC 110.9. In addition to selecting the appropriate circuit breakers and fuses, it's also important to coordinate the protective devices to ensure selective coordination. Selective coordination means that only the protective device closest to the fault operates, minimizing the extent of the outage and preventing unnecessary tripping of upstream devices. To achieve selective coordination, it's necessary to perform a coordination study, which involves analyzing the time current characteristics of the protective devices and adjusting their settings to ensure that they coordinate properly. The NEC requires that selective coordination be provided for certain critical circuits, such as emergency systems and life safety systems, as specified in NEC 700.27 and 701.18. Furthermore, ground fault protection is a critical aspect of industrial machine protection, as ground faults can pose significant shock hazards and cause equipment damage. Ground fault protection devices, such as ground fault circuit interrupters, or GFCIs, and ground fault relays, are designed to detect and interrupt ground faults. GFCIs are typically used in branch circuits to protect personnel from shock hazards, while ground fault relays are used in larger circuits to protect equipment from damage. The NEC requires that ground fault protection be provided for certain types of equipment such as service equipment and feeders, as specified in NEC 230.95 and 215.10. In addition to providing ground fault protection, it's also important to implement proper grounding techniques to minimize the risk of ground faults. Grounding involves connecting the non-current carrying metal parts of electrical equipment to ground, providing a low impedance path for fault current to flow back to the source. The NEC specifies detailed requirements for grounding electrical systems, as outlined in NEC Article 250. To further enhance the protection of industrial machines, it's also beneficial to implement preventive maintenance programs. Preventive maintenance involves performing regular inspections, testing, and cleaning of electrical equipment to identify and address potential problems before they lead to failures. Preventive maintenance activities can include inspecting wiring and connections, testing protective devices, cleaning electrical enclosures, and lubricating moving parts. By implementing preventive maintenance programs, one can improve the reliability and safety of industrial machines and reduce the risk of costly downtime. In summary, protecting industrial machines under NEC Article 670 requires a comprehensive approach that encompasses overload protection, short-circuit protection, ground fault protection, coordination, grounding, and preventive maintenance. By carefully considering these aspects and following the guidelines outlined in the NEC, one can ensure that industrial machines are adequately protected against electrical hazards and operate reliably. Let's consider some specific examples to illustrate how the principles of industrial machine protection are applied in practice. Imagine a large industrial motor driving a pump in a water treatment plant. This motor is rated at 480 volts, 100 horsepower, and has a full load current of 124 amps. To protect this motor against overload, a thermal overload relay is installed in the motor starter. The overload relay is selected with a trip current of 1.15 times the motor's full load current, as specified in NEC 430.32. This means the overload relay will trip if the motor current exceeds 142.6 amps for an extended period. To protect the motor against short circuits and ground faults, a molded case circuit breaker is installed in the motor feeder. The circuit breaker is selected with an interrupting rating of 65,000 amps, which is greater than the available fault current at the point of installation. The circuit breaker is also equipped with instantaneous trip and time delay trip functions to provide both short circuit and overload protection. To ensure selective coordination, the circuit breaker is coordinated with the upstream feeder circuit breaker. A coordination study is performed to determine the appropriate settings for the circuit breakers to ensure that only the circuit breaker closest to the fault operates. To protect personnel from shock hazards, the motor and pump are properly grounded in accordance with NEC Article 250. A grounding electrode conductor is connected from the motor frame to the building's grounding electrode system, providing a low impedance path for fault current to flow back to the source. A GFCI is also installed in the motor control circuit to protect personnel from shock hazards. To further enhance the protection of the motor, a preventive maintenance program is implemented. The program includes regular inspections of the motor and starter, testing of the overload relay and circuit breaker, and cleaning of the motor enclosure. Another example is an industrial robot used in an automated assembly line. This robot is powered by a 208-volt, 3-phase power supply and has multiple motors and control circuits. To protect the robot against overload, each motor is equipped with its own overload relay. The overload relays are selected with trip currents appropriate for the size and rating of each motor. To protect the robot against short circuits and ground faults, a circuit breaker is installed in the robot's main power supply. The circuit breaker is selected with an interrupting rating sufficient to interrupt the available fault current. To ensure selective coordination, the circuit breaker is coordinated with the upstream feeder circuit breaker. To protect personnel from shock hazards, the robot is properly grounded in accordance with NEC Article 250. A grounding electrode conductor is connected from the robot's frame to the building's grounding electrode system. A GFCI is also installed in the robot's control circuit to protect personnel from shock hazards. To further enhance the protection of the robot, a safety interlock system is installed. The safety interlock system prevents the robot from operating when the safety gates are open or when other safety devices are activated. This helps to protect personnel from injury during maintenance or troubleshooting. These examples illustrate how the principles of industrial machine protection are applied in practice to ensure the safety and reliability of electrical equipment. By carefully considering the specific requirements of each application and following the guidelines outlined in the NEC, one can effectively protect industrial machines against electrical hazards and ensure compliance with the applicable codes and standards. Always remember that electrical safety is a critical aspect of industrial operations, and it's essential to prioritize safety in all electrical work. Ensure that all electrical work is performed by qualified personnel with the appropriate training and equipment, and always follow the latest codes and standards. By doing so, one can create a safe and productive work environment for everyone. Let's examine the coordination aspect more closely, as it's a common area where issues arise, especially with oversized mains. Coordination, in the context of electrical protection, refers to the selective tripping of overcurrent protective devices such as circuit breakers and fuses to isolate a fault while minimizing the impact on the rest of the electrical system. The goal is to have the protected device closest to the fault trip first, leaving the upstream devices affected and maintaining power to the rest of the facility. When the mains are significantly oversized relative to the actual running amps of the connected equipment, it can lead to miscoordination. This is because the overcurrent protective devices on the mains may be set too high to effectively protect the downstream equipment. For example, if a main circuit breaker is rated at 400 amps, but the connected equipment only draws 100 amps, the circuit breaker may not trip quickly enough to prevent damage to the equipment in the event of a fault. In such cases, a smaller fault current may not be sufficient to trip the main circuit breaker, but it could still cause damage to the downstream equipment or create a safety hazard. To address this issue, it's important to perform a coordination study to determine the appropriate settings for the overcurrent protective devices. A coordination study involves analyzing the time current characteristics, or TCC, curves of the protective devices to ensure that they coordinate properly. The TCC curve shows the amount of time it takes for a protective device to trip at different levels of overcurrent. By comparing the TCC curves of the upstream and downstream devices, one can determine whether they will coordinate properly. If the TCC curves overlap, it means that both devices may trip at the same time, which is undesirable. To achieve selective coordination, the TCC curves of the downstream devices should be below the TCC curves of the upstream devices. This ensures that the downstream devices will trip first in the event of a fault. There are several methods that can be used to improve coordination in an electrical system. Firstly, one can reduce the size of the main circuit breaker to better match the actual load. This will make the circuit breaker more sensitive to overcurrent conditions and improve its ability to protect the downstream equipment. Secondly, one can use current-limiting fuses or circuit breakers. Current-limiting devices are designed to quickly interrupt fault currents, limiting the amount of energy that is let through to the downstream equipment. Thirdly, one can use zone-selective interlocking, or ZI. ZSI is a communication system that allows the overcurrent protective devices to communicate with each other. In the event of a fault, the ZSI system will determine which device is closest to the fault and instruct it to trip. Finally, one can use solid-state trip units with adjustable settings. Solid-state trip units allow for more precise control over the tripping characteristics of the circuit breaker. They can be programmed to trip at different levels of overcurrent and to provide different time delays. By carefully adjusting the settings of the solid-state trip units, one can achieve selective coordination. In addition to performing a coordination study and implementing appropriate protection measures, it's also important to regularly inspect and maintain the electrical system. This includes inspecting the overcurrent protective devices to ensure that they are in good working condition, testing the devices to verify their performance, and cleaning the equipment to remove any dirt or debris that could interfere with its operation. Regular maintenance can help to prevent electrical faults and ensure that the electrical system is operating safely and reliably. Addressing concerns about machines not built to the correct code section. If an assessment reveals that machines are not protected to the correct code section, several steps can be taken to rectify the situation. Firstly, consult with the machine manufacturer to determine if the machine can be retrofitted with the appropriate protection devices. Many manufacturers offer retrofit kits that can be used to upgrade the protection of their machines. Secondly, engage a qualified electrician or engineer to design and install the necessary protection devices. This may involve adding overload relays, circuit breakers, fuses, or ground fault protection devices. Thirdly, ensure that all protection devices are properly sized and coordinated. This requires performing a coordination study to determine the appropriate settings for the devices. Fourthly, document all modifications and upgrades to the machine. This documentation should include the type and rating of the protection devices, the settings of the devices, and the date of the modifications. Finally, train personnel on the proper operation and maintenance of the machine and its protection devices. This training should include instructions on how to respond to overloads, short circuits, and ground faults. In cases where machines are found to be non-compliant with the NEC, it's crucial to prioritize safety and take prompt action to address the deficiencies. Failure to do so can result in serious injury, property damage, or legal liability. Remember that electrical safety is everyone's responsibility, and it's important to take all necessary steps to ensure that electrical equipment is operating safely and reliably.